Okay, so limits. So to quick review, the minute somebody gives you a limit, you're going to do the first step. And what is always step one that I want to see, including on your handwritten work, anytime you do a limit? I'll open it up.
Direct substitution.
Very good. Direct substitution. And if you get something that's not a value like 2 or negative 57/11 or whatever, you get something like 0 over 0, then you better go do something. So one of the things that you can do if you get a 0 over 0, this last example we did, is if it's a special kind of function of more than one variable where you could rewrite it as a product of two functions that are functions of single variables, then you can individually do L'Hopital's rule if you need to on the separate factors, or direct substitution, or both. Another thing that comes into play is a theorem that you learned from Calc 1 that as the limit as theta goes to 0, sine theta over theta is equal to 1. That's a nice handy one. And of course you can use any of the limit facts that we've gone over from the past. So now we're going to get into some more advanced stuff. So if you end up with an indeterminate like 0 over 0, and you can't rewrite it as a product of two functions of a single variable, then you have to try some other tricks. And these tricks are from Calculus 1. So let's take a look at these in turn. And basically, it's if you can factor and reduce it, or use your knowledge of maybe rationalizing numerators or denominators in order to get an equivalent expression. And this is known as the replacement theorem in Calculus 1. So it's going to be the replacement theorem for my next two examples. So check this example 8, letter A. First up, direct substitution. What happens when I substitute in the point 4, 4?
0.
Uh-oh. I get 0 over 0, but that's indeterminate. Nobody knows what that is. That's meaningless. Can't use L'Hopital's because it's a function of two variables, and there's no way to rewrite it as a product of two functions of separate functions of a single variable. So here's the trick. You're going to use the replacement theorem. Well, how? And it turns out it works for this one, because I claim that you can rewrite this expression using algebra by factoring and reducing the lowest terms. Really? Yeah. Well, look at the denominator. You notice it's a difference of squares? And hopefully you guys remember how to factor a difference of squares. Yes? So how does x squared minus y squared factor? Any takers?
X minus y.
X minus y, and then what?
X plus.
Yeah. And it doesn't matter what order. That's those two factors. And then you're still going to take a limit as some arbitrary point xy approaches that fixed point 4, 4. Okay, then you'll go, oh, well, I can reduce this to lowest terms, you know, and we can factor out that 1. And now you can, and then this is what we're replacing. This is why they call it the replacement theorem, because we're replacing the original function that we're taking a limit of with this function, which is almost equivalent, and not quite, because they do not share the same domains, but it's close enough. So now what? Now use direct substitution. And so when you substitute in the point 4, 4 into this replaced function, I get a nice number, 1/8, and that happens to be the limit. Cool, huh? So let's do letter B now. Letter B, step 1, go ahead and do your direct substitution, only what's the point we're going to substitute in for letter B?
4, 1.
Yeah, this one you're going to substitute in x equals 4, y equals 1. So be careful when you're looking at one of these limit problems that you look very carefully at the point you're supposed to substitute. A common student error is to accidentally punch in some other point. It's like, uh-oh, what are you doing? So if I do direct substitution here, what am I going to get?
Over 0.
Yeah, so it looks like I'll get 4 minus 4 all over 2 minus 2. Oh man, 0 over 0. Indeterminate. Okay, now what? Well, this one, it's not as easy. It's not going to be like, okay, factor and reduce. Instead, what you're going to do is you're going to multiply by a special version of 1. And the special version of 1, and this is where you're going to rationalize, so the way you're going to pick this is in order to rationalize the denominator. So if you look at the denominator, it's the square root of x minus 2 times square root of y. So the special version of 1 is going to involve what's called the radical conjugate of that radical expression. So does anybody remember radical conjugates from an algebra class? And hopefully you learned that when you took Calc 1, when they made you...
flip signs.
Yes, right. So what would it be? What's my special version of 1 here? Tell me at least the summary.
X squared plus 2 square root y. Sorry, x square root x.
Okay, hold on a minute. I'm trying to figure out the actual special version of 1 here. So what is the radical conjugate of this guy?
Square root of x plus 2 times square root of y.
Right, it's square root of x plus 2 square root of y. Yeah. Now, why is that radical conjugate so awesome? Because it turns out when you multiply radical conjugate pairs together, you know, by foiling or what have you, you end up with an expression that no longer has radicals in it. That's the cool thing. Okay, so now we're going to multiply these two fractions together in order to do some algebra reducing here. And we're still going to take a limit, so I'm going to continue to write limit down here. So the denominator, you could FOIL it out, but I'm going to skip the foiling step and think a little bit. Doesn't this look like the product of a factorization of difference of squares? It kind of has that flavor of a minus b multiplied with a plus b. And I hope you say yes, because you know from your knowledge of difference of squares factoring that when you do FOIL it all out, you should get a difference of squares. So I claim the denominator, after FOILing it out, will look like a difference of squares. So the a is the square root of x, and the b is the 2 square root of y. And then the numerator, don't FOIL out the numerator. You're just going to end up in a world of hurt. So you want to kind of leave the numerator alone, although I'm going to do a little bit extra on the numerator and not FOIL it out. Don't do that, because you'll end up like a dog chasing their tail. You're going to get nowhere. You'll get into a world worse than the original problem. I am going to factor out a common factor of y from that first factor. So this isn't doing much, but you'll see why it's going to help me. So now when I look at the denominator and actually do the extra simplifying of squaring those terms, I'm going to get x minus 4y down in the denominator. I'm still not ready yet. And then the beauty here, and I hope you see the beauty for this problem, is you can reduce it to lowest terms. Voila. And this is where the replacement theorem is coming into the conversation. We're replacing the original expression with an equivalent expression that looks kind of different. That's for sure. But they're not exactly the same because their domains are a little bit different. But now you can use direct substitution on this new function here. So if I'm going to replace x's with 4 and y's with a 1, let's see what we get. So I get 4, and we're done. So the limit exists, and it's a 4. So any questions on that? Or the last two problems where we were lucky enough to be able to use the replacement theorem. That was awesome. Okay, you have to be good at algebra, you know, because algebra comes into play here. So be careful and show all your steps. You don't show me all of your intermediate steps and magically you get an answer. I'm going to go, I don't care if the answer is right and my math lab gives you full credit. I'm going to take away a whole truckload of points because I want to see that you know how to get to that result. Process matters in math, how you get to the answer. Okay, so now let's look at this problem here. We're going to find the limit of this. Now notice that both the numerator and denominator are trinomials, and they're special trinomials because the first term has x squared in it only, the last term has a y squared term in it only, and the middle term is an xy term. So both of them have that flavor. And you may have forgotten, but you were taught how to factor these special trinomials with two variables in it back in an algebra class. And if you forgot, well, I'm sorry. So we'll see. What I want to do is after we do the direct substitution, so I'm going to do it pretty quick. I always want to see that as your first step. It's going to turn out that this ends up being 0 over 0, which is indeterminate. So now you got to go do something, not L'Hopital's rule, because this is a hot mess and there's no way you're going to be able to rewrite this function as a product of two separate functions of a single variable. Sorry. So I'm going to stop the recording or pause the recording right now.
Dave mentioned it.
So I don't mind you using the diamond method to factor, but if you get wrong answers pretty often, then quit using it. Like learn how to do something else. I get people that could become very attached to the diamond method, even though I keep giving similar problems that involve factoring, and they resist learning something new, which is unfortunate. So please be open. While we're here, I want to now. Okay, so I'm going to go over not the diamond method, but something called the key number method. And some of you, I'm doing you a favor by showing you this right now. This is actually a Math 45 fact, knowledge, but some of you need it because it's been a while. So pay attention because you should be open to seeing new things. So there's a few students in the class who have even told me privately, oh, I like to do it my way. You know, whatever it is, the physics strategy or whatever. And it's like, well, that's really nice. And please be open to learning a new technique. Okay. So check out 6x squared minus 13xy plus 6y squared. The terms, the x squared and y squared terms, you're going to multiply the coefficients of those together to get your key number. So the key number for that numerator polynomial is 6 times 6, which is 36. Okay, so what? Well, now you factor 36 in all the possible ways you can, and there's quite a few factorizations. It's like, oh my goodness, we've got a few. And then you try to sum them up, and you hope that if it's factorable, that the sum will add up to the middle term. And it turns out that none of these factors add up to the middle term's coefficient because we want a minus 13. So this isn't going to work. So what you're going to try to do now is you'll start over because the key number is a positive number. There is another way to factor a positive number, a negative times a negative. And so we use those as our factors. And then you're going to hope that one of these rows, when you add or sum up the factors, you hopefully get the middle term's coefficient. And this is what I call bingo. This is not a technical term, okay? But that's your bingo. So the bingo numbers are -4 and -9. So what? What are you going to use your bingo numbers for? You're going to use them to split that middle term up into two as a sum of -4xy plus -9xy. That's what you use your two bingo numbers for. And then you copy down the first term and you copy down the last term. So this is an intermediate step. Then what? You factor by grouping. And this is another strategy you should have learned in some algebra class. You group the first pair together and you group the last pair together, and you factor out each of those pairs' GCF, greatest common factor. So the greatest common factor of the first pair is what?
2x.
2x. So if I factor out a 2x from that pair, what would the other factor be? Is that right?
Negative 3y.
Be negative 2y.
It's 3x minus 2y.
Wow. Oh, way back. How about 3x minus 2y? Is that okay?
Yeah.
Anybody have a problem with this, factoring? Or should we go over factoring in massive detail? I don't know. Depends on how bad you have it. Okay, so after factoring the first pair, now what? Well, you go plus, and then you're going to factor the second pair. Okay, does anybody see what the GCF, greatest common factor, is going to be for the second pair?
Negative 3y.
Okay, good. Why negative 3y and not positive 3y?
Because when you factor the negative out, you get the same as the first factored little pair.
Yeah, that's kind of the trick. Like, you could factor out a 3y here, but then you'll get negative 3x plus 2y, and this won't help you because you want to match the other factor, because you want to continue the factoring. So the more intelligent choice here, when you're factoring out the GCF, greatest common factor of that last pair, is factor out a minus 3y, and then you'll have the other factor is, and I'll use a colored pen. Oops, my eraser isn't working. It's going to be the 3x minus the 2y, like this. And then when you take a step back, you'll notice that 3x minus 2y is a common factor for these two terms. So you continue the factoring process and factor out 3x minus 2y, and then the other factor is 2x minus 3y. Is everybody okay with this? Did
Yeah.
everybody get something like that for your numerator? Okay, that's the key number method. You're going to do a similar thing for the downstairs or the denominator trinomial, but the key number for the downstairs trinomial is not 6 times 6, it's 6 times negative 12, which is, I think that's negative 72. So what factors of negative 72 will add up to the middle coefficient of negative 1? And I think negative 9 and positive 8 are the correct ones. So you would split this guy up into minus 9xy plus 8xy, and then you would copy down the first and last terms, and you would factor by grouping, and you should get, if everything goes well, 3x plus 4y times 2x minus 3y. Okay? So why is that significant? Because when you put all your hard work together of all this factoring, then you can reduce this expression to lowest terms. And then using the replacement theorem, you just take use the replacement theorem on that expression. So you're going to take the limit as the point xy approaches the point, the point 32. Oops, I almost had that backwards. And then you substitute in x equals 3 and y equals 2 into this expression, and hopefully you get something that isn't indeterminate, and it turns out we do get 5/17. Okay? Any questions on that, or comments, or issues? Okay? All right. So now let's jack it up some. What about functions of 3 variables? You can do limits for that too. You use the same kind of procedure and approach. Here you have an ordered triple approaching the point 1, negative ln 2, 3. Oh my goodness. Well, try direct substitution. So in place of the z, you'll substitute 3, e to the xy power, so e to the 1 times negative ln 2, and then clean this up. What is that? You don't get full credit if you leave it like that, not in my book. So it turns out that e to the negative ln of 2 is 2 to the negative 1 power, or a half actually. So this is going to be 3 over 2, and we're done. So letter A is easy, the limit exists, and it's just 3 halves. Cool. Are they always that easy? No, forget it. Well, now keep going. What about this letter B here? The ordered triple XYZ approaches 1, 1, 1. What happens when you substitute 1, 1, 1 into this function of 3 variables? Oh my goodness. Oops, I'm going to run out of room here. You get 1 plus 1 minus 1 minus 1 all over 1 minus 1. I get 0 over 0. Oh goodness. What the heck? That's indeterminate. So what should we do now?
Factor.
You're going to factor, but it's another technique that you should have learned from your old beginning algebra days. And so you're going to factor by grouping again. So this is the trick, essentially. You are going to use the replacement theorem, but do you remember how to factor by grouping? So now for those of you who, you're like, oh, wow, this is so dumb that we're even factoring by grouping. Oh my God. Listen, factoring is really important. And if you think that it's going away, like, oh, that's just an algebra skill, hopefully I never see it again. If you take differential equations, which is Math 253, half the class is factoring. You factor polynomials of higher degree than just 2. Like when I teach it, you have to factor polynomials of 3, 4, 5, 6 degree. And then also when you do exact equations and when you're trying to find an integrating factor that's going to work, if you don't know how to factor, and factoring by grouping is key, you're going to be hurting. So it's a very, very, very important skill. It's integral to mathematics. So nobody's going to pay you to factor a polynomial, I'll tell you that. But so if I factor out the greatest common factor of the first pair, I get x, and then the other factor is x plus y. And then the other pair has, and the most intelligent thing to pull out is a negative z, because then the other factor is x plus y. And then, oh my goodness, x plus y is common to both of those terms. So I pull out an x plus y, and the other factor is x minus z. So why is that great? Because now when I rewrite the expression where the numerator is factored completely, oh, am I losing power again? Hang on a second. Excuse me a minute, I'm having technical difficulties. Let me put it on pause. Does anybody have this problem? Christmas is coming up, and I want a new Christmas present. I want a new laptop. I already have 2 laptops. So I asked my husband for a laptop, and he goes, you already have 2? I go, yeah, I want another one. He goes, how many do you need? I go, as many as it takes. All right, yeah, the cord, there's something wrong with this cord. This is crap. Okay, so factor by grouping. All right, here we go. So now what? Yeah, it's the cable. You don't want to know, Vanessa. Don't even ask questions that you don't care about. It's terrible. It's just terrible. Okay, so now, hey, I can use the replacement theorem. Why? Because, hey, it reduces. So now what? Well, we'll take the limit of x, y, z as that ordered triple approaches 1, 1, 1. And hey, now when we do it, and this is really tough. I don't know, this might be beyond my pay grade. What's 1 plus 1?
2.
2.
2.
Ah, wow, thank God we got somewhere. All right, so 1 plus 1 is 2, and it looks like that limit exists, and it's a 2. Woohoo! And so again, the point is you got to know your algebra. If your algebra is good and you know how to factor and do some other things like rationalizing denominators and all that good stuff, you should be fine. All right, so whew, done with that problem. Now let's talk about the harder problem. How do you prove a limit does not exist? It's not that hard. I'm going to show you the procedure. On your MyMathLab quiz, that's quiz 4, Sunday, you are going to have a problem where you have to show a limit does not exist. If you do not show me all of your intermediate steps and you don't have proper notation, even if your MyMathLab answer gives you full credit and full points, I will take away points from you. And I'm telling you in advance, that's how I roll. I want it all to be nice. Guessing is not good. You know, guessing is not going to cut it. Okay, so let's talk about what you do know. But basically, when you took a Calc 1 class back in those days, I don't know if you remember. Let's say you had a function here, you know, have you ever seen these absolute value functions that look like this, like y equals x minus 1 over x minus 1? Have you ever seen those?
Yes.
Something
Yes.
like that? Okay. So you've seen those. So like a lot of times what you'll see is you'll go, okay, it's like -1 up into a point, and then it's like +1 after that, or something like that, okay? And so when they ask you to take the limit of this as x approaches 1, the left-hand and right-hand limits don't agree. Well, why not? Well, as you approach the 1 from the left, the limit is -1. But when you approach the 1 from the right, the limit is +1. And so you end up getting the limit does not exist because the left-hand limit does not agree with the right-hand limit. Does this ring a bell for any of you from your old Calculus 1 days, I hope?
Yes.
Yes, it does.
Definitely.
Does. If
Just
it
ring the
does,
old bell.
yeah, one of those old bells. Ding dong. Yeah, oh God. Yeah. Then you're going to be totally understanding what we're doing here for the most part. I hope I try to make it easy. So here's the big deal, what the analogous situation in Calc 3. In Calc 3, we don't have an interval. So you can't approach a single number from the left or the right-hand side. That doesn't fly. This is a Calc 1 kind of thing where you approach from the left or right. But we don't have, there's no such thing as approaching from the left or approaching from the right. There's no such thing. Well, what do you mean? Because we have an arbitrary point approaching our fixed point, and we could approach it from infinity directions. Really? Yeah, like check out that next page, what we're talking about. So if the value of the limit as xy approaches the fixed point x naught y naught of f of xy equals L is not the same for all possible approaches or paths, then we can say the limit does not exist. So here's the xy plane. Let's say right in the center of your disk there is your fixed point. Do you see that you can approach it from infinity directions? You can come at it at that fixed point from all directions?
Yes.
Yeah, so there's no such thing as, oh, left-hand limit, oh, right-hand limit. Oh, those days are gone, people. Well, what does that mean? Do I have to show that all infinity paths don't agree? Thank God, no. That would take us infinity time. Good news, you only have to choose 2 paths, and those paths are usually given to you. Also, it's like handed to you on a silver platter. Thank God. If you can show that the 2 paths that you're handed, that you get 2 different values, that's good enough for government work. Then you conclude, the limit doesn't exist because on these 2 different paths, I get 2 different answers, and that's good enough to prove the limit doesn't exist. So that's how you're going to do it. Now, folks, for these problems that I'm about to do, you basically are doing a mini proof to show that the limit does not exist. So I want to see all the steps. Don't skip steps. So here we go. Example 11. You're basically doing a mini proof here. So we're going to show that the limit as xy approaches the point 0, 0 of this funky function of 2 variables, wow, does not exist. And we're going to evaluate the limit along 2 different paths. And remember, there's infinity paths. Thank you, God, they're giving you those 2 paths. That's taking a lot of the work and guesswork out of that. So one of the paths is you're going to approach the fixed point 0, 0 along the x-axis. So here's the fixed point that we're trying to approach, 0, 0. Now remember, you could approach it from all infinity directions, but thank God we don't have to do that. They're saying, hey, here's the x-axis. Get really, 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 really close to that point, 0, 0, approaching it on while you stay on the x-axis. Now, what do you know about being on the x-axis? Isn't it true that when you're on the x-axis, y is 0 the whole time? Please say yes.
Yes.
That's going to be your key to getting the answer for letter A. that if you stay on the path of the x-axis only, you know, whether you approach from the left or the right to your fixed point, y stays 0 the whole time. So watch how I'm going to do letter A. I want to see all of these steps. So you're going to copy down this lim. I want you to copy down the word lim, and you're going to copy down the actual function, but not all the way. Everywhere I see the letter y, and there's a few spots where I see a y, instead of putting the y there, I'm going to replace y with what?
0.
0.
0.
And then here, this part is going to be, you're going to say, instead of any old point x, y, you're limited to points that have any x coordinate, but the y coordinate is forced to be 0 because we're going to stay on that specific path where the y coordinates are zeroed out. So this is the intermediate step. And then I'm not going to do direct substitution. Okay, you end up never doing direct substitution here. Okay, if you do, you're going to get screwed. You hold off, but you keep writing down the word lim, and here you're going to write down the point x0 approaches that fixed point 0, 0. And then, you know, 0 squared is just 0. So you'll have x squared over x squared squared because of this thing. And then what is x squared over x squared reduced to? Quick.
1.
Thank you. So you're really just asking, what is the limit of 1 as x0 approaches 0, 0? Well, you know from Calc 1 that the limit of a constant is what?
Constant.
The constant. And there's your answer for letter A. So if we stay on the x-axis path and we approach our fixed point 0, 0, it seems like the limit is the number 1. Okay, save that for later and move on to part B. Part B says, hey, do the limit all over again, only this time you're going to try approaching your fixed point of 0, 0 from a different path. The path is going to be along the diagonal line y equals x. So if you graph the line y equals x here, I'll put a dotted line here, there's y equals x. So now the approach to our fixed point, which is the origin for this problem, is we're going to stay on that diagonal line, y equals x, the whole time, and then try to see what the limit is going to be. Now, when you're on the diagonal line y equals x, x is the independent variable, so he could be anything he wants, but y is dependent on x, so y is an x. So what you're going to do here is you're not going to put the xy approaches 0, 0. Oh, no, 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 no. Because here, the variable y, as long as you stay on that dotted line, is always going to be what? X.
X.
So you're going to have xx approach 0, 0. And so then when you copy down this function here, you're going to replace all of the instances of y with what?
X's.
X's, yes. Because if you stay on this particular path, this diagonal line, all your y values are going to be whatever x is. And now you never use direct substitution here. You used to simplify using algebra. What is x squared minus x squared end up simplifying to?
0.
So you're going to have 0 in the numerator, and then 1 apple plus 1 apple, you're going to just combine like terms here, is 2 apples. And then, but 0 divided by something other than 0, because when you take the limit, you just get close to the 0, but not really, is going to end up being a constant. This is always going to happen, folks, when you do one of these problems. You'll get a constant. But the limit of a constant is?
The constant.
A constant.
The constant. And then do you notice that since the limits do not agree, this is your conclusion, and I want to see the conclusion. Be an attorney and actually plead your case. You know, Your Honor, my client is not guilty because, and then say, since the limits do not agree, we can conclude the limit does not exist. Okay? So you have two different paths, and you get two different results, so therefore you can conclude the limit can't exist because you get these two different answers. That's not cool. For the limit to exist, you have to get the same result, yeah? And that's how you prove a limit does not exist, okay? So have fun with that kind of problem and do a few so you get the feeling of it before you actually take your quiz, okay? Questions?
I'm good.
Okay, everybody okay? So we're doing a lot of review of Calc 1 today. Interesting. Okay, now let's do limits using polar coordinates. Review of Calc 2. Cool. It turns out that there's some limits where you're trying to find a limit of a function of more than one variable, specifically a function of two variables. And if you can't use the replacement theorem because it doesn't factor, it doesn't factor and reduce, it's already reduced completely, and you can't use that trick of rationalizing denominators or rationalizing numerators because there are no radicals, factoring by grouping doesn't work. It's, you could try an alternate technique, and that is convert to polar coordinates and then take the limit. But this is very restricted to certain very special cases. So be careful you don't just use it any old time. Here's the criteria. If you're going to convert to polar, the limit has to be where r goes to 0. So, so that means that you have to limit it to where xy approaches the fixed point of 0, 0. So if you are trying to evaluate a limit where the fixed point is xy approaches 1, 1 or 1, 2 or something other than 0, 0, this technique won't work. So you need this to be your fixed point. So it's limited, but oftentimes when you are doing these limits of functions to variables, the fixed point oftentimes is 0, 0. So that's kind of cool. So then you can use this the polar coordinates technique. Now, one of the things that you should remember from your Calc 2 days, but I know it's been a while, so you may have forgotten your polar coordinates already. The conversion formulas are these. X is equal to r cos theta, and y is equal to r sine theta. And I want to let you know something kind of cool is that we are going to be doing a lot of polar coordinates this semester in about a month or two. So if you think, oh, that stuff we learned in Calc 2 is a waste of my time, and oh, yeah, sure, we're using it right now for a brief moment, but we'll never see it again. I got news, we're going to see it a lot, and you're going to be using it like all the way through to the final. So, just so you know. Okay, so here you go. Let's check it out. First, direct substitution. How do you know that we even need to use any technique if you don't try to first see what you get at your first crack, which is direct sub. And unfortunately, I get that indeterminate. It's like, oh, indeterminate, 0 over 0, now what? Well, you can't really factor the numerator in it. You could try. And please don't do illegal canceling. Like I've seen students even in Calc 3 do this. Hey, look at this, x squared and x squareds cancel and the y squareds cancel. Woohoo, I'm done. No. Why is that illegal canceling?
It's the addition signs.
Yeah, you have plus signs in between here. Now, if those were all multiply symbols, then I would say, yeah, then you have factors that can, you factor out a 1 essentially. But here, no. So don't do anything silly like that because then you're going to hurt yourself. And even if you did get, luckily, the right answer, I'm going to take away all your points for pure luck. So what do? You start converting all of this to polar. So when you convert to polar, all you do is start replacing all of the x's with r cos and all of the y's with r sine, okay? Before I do that, though, let me remind you that there's one other conversion that you can save yourself some time. I mean, we could put all the x's with r cos and r sine for y, but once you notice there's another conversion that x squared plus y squared reduces to r squared. So you can, knowing that, this x squared plus y squared you can replace with r squared, and the same with the denominator, so that's nice. But then that third term in the numerator, no, you can't, you have to do it by brute force. So the x squared gets replaced with r squared cos squared, and the y squared gets replaced with r squared sine squared, and you take the limit as r goes to 0. And that's why you need that criteria that your xy point approaches the fixed point 0, 0. So what happens when you do this? Well, substituting in r, equals 0, hold on a minute. This is not going where I wanted. Hang on a second. Don't use direct substitution yet. Hang on a second. Let's do some factoring. Otherwise, we're going to get 0 over 0 again. We don't want that. So we're going to use the replacement theorem while we're doing this. So you'll notice if you multiply these two factors together, you'll have r to the 4th cos squared sine squared, but it does have a common factor of r squared. So when you factor out your r squared, the expression looks like that, and then reduce that to lowest terms. So you're really just taking the limit as r goes to 0 of this expression, and now you can use direct sub. So you go, okay, 1 plus 0 squared times, anything is 1 plus 0, and the final answer is 1, and the limit exists, woohoo, and you win the game. So that helped to convert to polar to evaluate that limit. And yes, it's going to be like on the quiz and the homework. Don't even ask. Yes. Now, it's in the book too. Go read about it. Now here, if you use your direct sub and you're like, oh, okay, I get 0 over 0, now what? You could try rationalizing the denominator, but I don't think it's going to help too much because the sum of squares, x squared plus y squared, does not factor nicely. So what you're going to do is convert to polar, because we do have the criteria xy goes to 0, 0. So you're going to take the limit as r goes to 0, and the numerator is r cos theta minus r sine theta. The denominator is the square root of x squared plus y squared, but remember x squared plus y squared is r squared. And so when you reduce this to lowest terms by factoring out an r from the numerator, I'm getting kind of messy here, and then square root of r squared is r. Once again, the r's reduce, you cancel, and then you're left with, take the limit as r goes to 0 of this expression, cos theta minus sine theta. Uh-oh, now what? Well, we're taking a limit as r goes to 0. Nobody knows what's going on with the thetas. So the answer is does not exist, because theta could be going all haywire. And so then you can rightfully conclude that the limit does not exist. And we're done. Very cool. Questions?
With the square root of r squared in that last example, it just assumed to be the absolute value of r, right?
Yeah, yeah.
Okay.
We're going to assume r is positive. Okay.
Did you deal with the cosine and the sine in the first problem?
Well, it multiplied with 0, my dear.
Oh, okay.
R squared 0 times cos theta sine theta. 0 times anything is 0, right? Hello?
Yeah.
Okay. Ask Kasara, your bearded dragon. She knows.
Okay.
Any other questions?
I just want to make sure it's does not exist just because it could be in any quadrant.
Well, yeah, you don't know what your theta is doing. R approaches 0, but our, theta could be going all over the map. Who knows? You have no accounting for theta.
Got it. Thank you.
Mm-hmm. Yeah. So, some of these surfaces, who knows what they look like? I mean, shoot, x minus y all over the square root of x squared plus y squared. It's anybody's guess. I mean, what we could do is I always like to go to my software, although you could go to GeoGebra, which is the online 3D version, and graph some surfaces here. So I'm going to go z equals, let's just see something, what we get here, x minus y divided by, let's see, what is that, square root, just hold on a second, I know there's a square root here. Square root of x squared plus y squared. I have no idea what this thing looks like. It could be pretty funky. Ooh, that's kind of pretty. Check that out. Can you guys see that okay, or is it coming through okay?
Yes.
Okay. It's kind of looks like an egg carton or something. Let me change colors. Ooh, that looks really cool. So you might notice that if you look kind of closely there, there's sort of a hole along there, and that's probably that the reason why we get DNE is we're approaching the origin, but it doesn't look like the surface exists there because there's like a cut through there, like a slit. If you can kind of see that pretty well. If you're having trouble seeing it, let's see if I change colors, maybe you can see it better. Ooh, I don't know, that doesn't help. How about turquoise blue? Ooh, now you can kind of see the slit there in the middle of that surface. So that kind of gives you an inkling as to why the limit's not existing, because there's no surface there. There's no there. Pretty cool, huh? So that there you go, taking limits of functions of two variables. Fun times. Okay, now briefly to finish out this section, continuity. Continuity is pretty much like domain. Like if your function, as we can see from that nice diagram there, we just graphed the surface, the function isn't continuous at 0, 0. It doesn't even exist there. So your function, to be continuous, this is the official definition. As xy approaches the fixed point, x naught, y naught, the limit has to be, basically direct substitution has to work perfectly in order for you to have that continuity happen. You know, and it has to happen without the replacement theorem. The replacement theorem, that doesn't really mean you have necessarily have continuity. You still could have a hole there. That's what you were using the replacement theorem. So this function here, which we did earlier, and I think we got does not exist. It's not continuous at 0, 0. Or wait a minute, the limit at the, oh, wait a minute, I proved that one. The limit did exist. It was 0, but there is a discontinuity there, but it's a hole. So really? Yeah. Anyway, so we call that removable. I don't know if you guys remember from Calc 1. I'll draw a picture. Do you remember that if you had, Calc 1, where you had a hole in a function, let's say you had the hole at 2. And do you remember that the limit of the function as x approached the hole was still good? Like let's say the y coordinate of that, I'm making something up, was 3. So the limit would still exist even though you had a hole, even though the function wasn't defined at the hole. Does that ring a bell?
Yeah.
And so the hole, they called holes removable discontinuities because I always tell, when I teach Calc 1, I say I could consider it removable if you spray some Fix-A-Flat in there. I don't know if you guys remember fixing a tire, Fix-A-Flat, you know, and it fixes the hole real quick, so it's removable. On the other hand, this thing, I think we went off to infinity because the surface ended up looking kind of like a volcano, so that at 0, 0 it had like this asymptote, and that is a non-removable discontinuity. Okay, so if they ask you on MyMathLab to discuss continuity, the good news is just pretend you're being asked to find the domain of a function. So let's finish off with this last example here. Discuss the continuity for the function f of xy is equal to 2 divided by y minus x squared. Well, how would you find the domain of this? Do you guys remember finding domains earlier in the section?
Denominator.
Expression can equals 0.
Yeah, you're basically saying that, which you can rewrite as this by adding x squared to both sides. They both mean the same thing. So you don't want y to be equal to x squared. So you want to, if you were to graph the domain in the xy plane, you would basically shade everything in, but you wouldn't shade in the parabola, so you put a dotted line there. That parabola would be off limits. You could feed the function any point except for points that live on that parabola. Okay, everything else is fair game to plug in. So if you did this using set notation, you would say, oh, he's continuous everywhere except if y is equal to x squared. Okay, so that's how you would do it. So he's continuous on this set. And I'm using set notation. And he's discontinuous anywhere else. This is a non-removable discontinuity because it's not just a simple hole. You know, you couldn't put enough Fix-A-Flat on that infinity parabola to fix your tire. not going to work. Okay, so that's a non-removable discontinuity, the whole parabola. Okay, so I think this is a good place to stop. I'll stick around for questions or concerns. Remember, I have an office 2 hours today at noon. You're welcome to come. If not, remember Monday is my holiday, not the campus, but I'm going to be gone. You're to watch a whole bunch of videos by me that I specifically made for you here in week 6. You're going to watch these 5 partial derivative videos. So please watch those on Monday, because I'm not going to do those on Wednesday. I'm going to assume that you watched them all. And on Wednesday, we're going to continue going. So if you don't know how to take a partial derivative by Wednesday of next week, ooh boy, life will be rough. Okay, so on that note, see you later. Bye.
Happy holidays.
So much.
Thank you.